In this lecture, we take a look at two more examples involving the calculation of electric potential difference in constant electric fields. Sometimes these examples can be initially a little bit confusing. I follow always a particular strategy, especially when calculating potential difference. Follow the math. Once you follow the math, that then tells you what has to happen. So for example, let's take a look at the first of these two examples. Please copy it down into your notes as I read it here. Okay, a uniform electric field of 300 newtons per coulomb points in the negative x direction. So rather than taking the constant electric field and pointing it downwards, in this particular case, we're going to point it to the left. So let me go ahead and construct here a little coordinate axis like so. You'll see why as I get deeper into the problem as I read it. Okay, and then right here is a uniform electric field, for example, pointing to the left. So now in vector form, let's immediately write E as negative 300 I hat newtons per coulomb. Okay, there are 3 points of interest on the diagram, points A, B, and C. Point A is in the second quadrant, negative 3 and positive 4. So that's kind of roughly like so, negative 3, positive 4. Let's say it's about right here on the diagram like so. That's point A. Okay, point B is in the first quadrant on the diagram. 4, 4 is its coordinates. So over 4 and up 4 like so. This is point B. Okay, and then point C is at 4, 1. So let's go over 4 and up 1. Let's position that here. Right here is point C. Let me go ahead and write down these coordinates here while I'm at it. So negative 3 and positive 4, positive 4 and positive 4, positive 4 and positive 1, like so. Okay, now recall that the equipotential surfaces are always perpendicular to the field lines. So then therefore right here, for example, is an equipotential surface, and right here is an equipotential surface. Okay, now what we're going to do in this problem is find the potential difference between these various points on the diagram. It says find the following potential differences, VBA, VCB, and so on as we move through the example. Now, as we do move through the example, here's a portion of the equation, or the portion of the equation, that we're going to use in order to calculate these potential differences. VB minus VA is equal to the following dot product. Notice that I am not writing this as an integral sign on the right-hand side, and the reason for that is because we have a constant electric field, and then we're going to have a displacement vector here, delta L, which we'll just simply think of as a straight line. So this is kind of like doing dot product calculations for calculating work, for example, for constant forces way back when in the beginning of chapter 7. Okay, now let's take a look at part A of the problem. Notice the notation here, V capital B A. What this specifically means is that in this calculation, point B is the final position and point A is the initial position. That's how this notation relates to this. So point B is the final position and point A is the initial position. And then we're going to calculate the potential difference, final minus initial, by setting up and calculating this dot product. So what is the displacement vector delta L then? Well, very simply, delta L always goes from the initial position to the final position. So then therefore on the diagram, the delta L vector is like this. It has a total distance of 7, and it's in the positive x direction. So I'm not going to draw the delta L on this diagram, because if I did for the remaining portions of the problem, then it would start to get a little bit crowded. But the delta L displacement vector from here to here is positive 7I hat. Like so, okay? It's going to be in terms of meters, by the way, because we're working in metric SI units. Like so. Okay, and now, as I said, we just follow the math. So VBA is equal to negative, and then dot product. Negative 300 I hat dot positive 7 I hat. And then ultimately you'll end up with Newton meters per coulomb. That's a joule per coulomb. It's going to be in terms of volts. Okay, so the negative signs here cancel out, and we end up with positive 2100 volts. So the potential difference is a positive number. Final minus initial is a positive number. So this then means that we had to move from a region of low potential to a region of high potential. The easiest way to think of this is in terms of a positive test charge. in which direction does a positive test charge always fall? It always falls from high to low potential. So then therefore a positive test charge would fall from here to here on the diagram. Therefore the potential difference as we go from here to here, low potential to high potential, has to be a positive number, as it is. So once again, you just follow the math, and then the math tells you what has to happen. Okay, watch this occur for the remaining part of the example. Okay, now part B. Okay, in part B, take a look at the notation, VCB. What that means, let me get rid of initial and final here from earlier. What that means is that point B is now the initial position, that's right here. This symbol here corresponds to that. So point B is the initial position, like so. And then point C right here is the final position, like so. And then we need to find the potential difference as we go from here to here. Now, it should be 0 because we're moving along an equipotential surface. But if you didn't know that ahead of time, just once again, follow the math. So let's go ahead and write down the calculation by getting our displacement vector delta L. So the delta L goes from here to here. You'll notice that it's 3j hat, like so, but it's negative. So then therefore, I'm going to write the delta L as negative 3j hat meters. And then we just set up our dot product. So the potential difference is going to be negative and then E dot delta L. Negative 300 I hat dot negative 3 j hat. Remember that I hat dot j hat is equal to 0. And then therefore there's no potential difference between here and here because after all, it's an equipotential surface. Once again, the math then, once you do it correctly, it tells us what has to happen. Okay, and then lastly, I need to move my file. Okay, so let me erase. So. Okay, and now lastly, for part C of the problem, we're asked to calculate VCA. In other words, point A on the diagram corresponds to our initial position. So that's right here, like so. And then point C on the diagram, that corresponds to our final position. That's right here. So we're going to find the potential difference as we move from here to here. It should be the same thing as part A of the problem, positive 2100 volts. Because after all, we're going from this equipotential surface to this equipotential surface here. But if you didn't know that, or if you intuitively didn't understand that, then just once again follow the math. So let's go ahead and write our displacement vector delta L, which looks like this. So our delta L is going to be a positive 7 I hat and then minus a 3 j hat, like so. So delta L is positive 7 I hat minus 3 j hat in terms of meters. And now we just do our dot product. So negative, and then E dot delta L, like so. So the negative signs here cancel, and then ultimately we end up with 300 times 7 once again, and this then gives us positive 2100 volts. Like so, and that makes sense. If you put a positive test charge here, it would fall from high to low potential. So then therefore, as we go from here to here on the diagram, the potential difference should be a positive number. Final minus initial should be a positive number, and it is. Once again, you follow the math, and that then tells you what has to happen. That's how I always learned electric potential when I was a student. When I was a student, it really tripped me up initially as to what it was that the calculations meant. What you do is you just do the calculations, and then when you get to the end result, that then tells you what has to happen. Okay, now let's take a look at the second problem for this lecture. This is actually a really easy problem that we'll take a look at, but it's a specific application, and it's the parallel plate capacitor. Okay, let me go ahead and do some erasing here. Okay, let me move my file. Okay, reading the problem, copying it into your notes. Find the potential difference between two parallel plates with identical but oppositely charged area charge densities sigma. We'll ignore edge effects. Okay, the distance between the two plates is referred to, or sheets as they're sometimes called, is D. And then this is the voltage of a parallel plate capacitor. So here's what's being described. Okay, so right here we'll say is the positive plate or sheet. Right here is the negative plate or sheet, and then therefore the constant electric field points like so. Okay, recall from a Gauss's law calculation that the magnitude of the electric field is sigma over epsilon naught. Okay? Okay, and now the plate separation is this distance here. It's referred to as D. It's asking us to find the potential difference between the two plates. It doesn't matter, however, which way we do this. That is, we can go from here to here, or we can go from here to here if we wish. Depending upon which way we move in the problem, that will then tell us the potential difference is either a positive number or a negative number. But it's the number itself that matters, the number of volts. Okay, now this is a basic calculation that all students have to be familiar with. So then therefore, let's set up the problem using the following expression. Okay, once again, it's a constant electric field, so then therefore I don't have to worry about an integral calculation. We can set up the problem like this. Okay, let's call this right here point A, this right here point B, and then therefore my delta L vector will be from here to here on the diagram like so. Like this, okay? Okay, now if we're going from here to here, we're going from low to high potential. So then therefore the number that I should calculate should be a positive number. Final minus initial, high, low should be a positive number. Okay, the potential difference in the context of the parallel plate, by the way, is usually just referred to as V. So let's go ahead and write that here. And then we're going to have the following. There is a 180-degree angle between E and delta L. So then therefore, cosine of 180 when we do our dot product is equal to -1. That negative sign will cancel with this negative sign here, and then all that we're left with is the following, E times D. So once again, we did a dot product here. There's a 180-degree angle between these two vectors. Cosine of 180 is equal to -1. That negative sign cancels with this right here, and then we just simply end up with E times D. Commit this expression to memory because it will become important later on, specifically when we start talking about capacitance and types of circuits that contain capacitors. V is equal to E times D. It's easy to remember, especially if you have a friend whose name is Ed. So always just remember the following phrase. What's the kid's name? The kid's name is Ed. What is the potential difference for a parallel plate capacitor? It is E times D.